Hey, it's Mrs. Cat, and we are going to take the labs that we've done exploring gas properties, which was the video station lab, and KMT and properties of gases, which was the graphing and CER activity, and we will summarize all of our gas relationships together in kind of a modified 3 levels chart. So in both of those labs, we looked at 4 properties of gases: volume, amount of gas, temperature, and pressure. And before we go into the relationships, I want to make sure that we have these defined. We're going to think about these on 2 levels. We're going to think about these with macro level and particulate. Okay, so I also want to make sure that we know what our variables are as well as their name, as their abbreviation. So volume is capital V. At the macro level, this is how much space a gas takes up. Okay. Remember, at particulate level, this is the space between particles. Let's see if I can move this over a little bit so that's not in our box. Perfect. Okay, amount of gas is signified with a lowercase level n. We actually don't have a macro way to define this. This is moles is also a way that we've seen this. We'll talk about the mole a lot later in the semester and second semester, but for now, we're just going to define this as the number of particles. And that's just at the particulate level. Okay. Temperature, as we know, is capital T for our symbol. This is how hot or cold something is at the macro level. And at the particulate level, this has to do with the speed of particles. Okay. And then finally, pressure, capital P. This is a push or force that a gas exerts. As far as our macro definition. And then remember, this is one that is really commonly confused or a misconception, is pressure at the particulate level. And this has to do with particle collisions. Okay, I want to add in here that for temperature and pressure, that we want to show what's happening with speed of particles and collisions of particles. And remember, we do this by showing whooshies to show changes in temperature because of speed, or speed because of temperature, and then pressure is our whammies to show our particle collisions, right? So we'll have a line, or we would have a zigzag for each of those. Right? Okay, we have 6 relationships that we're going to take a look at. We'll do a few in this first video. I'll do a second video for the rest. But when we look at these 6 relationships, we are going to look at just 2 variables at a time, where the other 2 variables stay constant. Okay, if we change one, something else is going to happen. But to keep this simple as we can, we're going to look at just 2 variables. Okay, so we're going to start with pressure and volume. Okay? And this is going to be when the amount of gas and the temperature are constant. So when we define our relationship, we're just going to look at the 2 variables that are changing. The other 2 variables that are not listed in the relationship are going to be assumed to stay the same, be constant. Okay, we're going to keep this pretty simple. Our relationship that we've seen through the lab is that as volume increases, pressure decreases when moles or amount of gas and temperature are constant. Now I'm abbreviating, obviously using my variable symbols here, and increases up, decreases down. I'm going to move this R over a little bit so we know that it's amount of gas and temperature, not tare. Okay, so Macroscopic examples, I'm going to kind of let this be up to you, and I'll give some suggestions, but these could be things from the lab that we saw with the stations lab in the videos. This could be some examples that you know in real life. But as far as the lab is concerned, the marshmallow in the syringe is a good example of this. Marshmallow in syringe. Right? As it was pulled out, the marshmallow got bigger, okay? Because the pressure went down as you put the syringe in, the marshmallow got smaller because the pressure went up, okay? So we want to show this as, again, volume goes up, pressure goes down. We're not going to focus on the amount of gas and the temperature. They're going to stay the same. Okay. In our symbolic, we really want to focus on that graphical relationship. Okay, so I'm going to sketch my graph like we had from KMT and gas properties. Okay, so here we want to go pressure and volume here. Again, we always want dependent variable on the y-axis and independent variable on the x-axis. So our curve is going to look like this. Okay. We want to say that this is an inverse proportion. And then we can maybe show a little example here. Let me change colors. So let's say the volume is going to increase by a factor of 2. Because it's an inverse proportion, that would be like taking the inverse of 2, which is 1/2, and that would be the factor at which the pressure would decrease. Okay, we'll look at this a little bit more as far as the symbolic when we do the VNTP tables to do calculations. Okay, particulate, we're going to draw 2 particle diagrams. Let me change colors back here. So I'm going to show 2 different volumes by showing 2 different containers. Right? One bigger, one smaller. We want to keep number of particles the same. I'm just going to choose a small number of particles. I'm going to use 4 particles. 3, 4. 1, 2, 3, 4. Okay. Temperature stays the same, which means we're going to have the same number of whooshy lines, same number of tails on our particles. I'm just going to keep it at 1. Okay. The difference is going to be the number of whammies. So we want to show more pressure in the smaller volume. So I'm going to show 2 collisions happening. Let's go 1 whammy there. Let's go 1 whammy there. And then I want to show my motion lines on my other 2 particles. Okay. Because the particles have more space to spread out, and they're going to be moving at the same speed, we're going to have fewer collisions in our larger volume, which is why the pressure decreases. So I want to go down to 1 collision and then show the motion of my other particles with 1 whooshy line. Okay, so same number of particles. Same speed. More collisions versus fewer collisions. Okay, awesome. That's our first relationship. Take a look. We're also going to focus on pressure here as the dependent variable, but this time we're going to change the amount of gas. So amount of gas is our independent variable. Actually, let's be consistent here. So I'm going to say as amount of gas, which is N, increases, pressure will increase if volume and temperature are constant. Okay, let's take a look at the macroscopic example. This could be seen with air blowing something up, right? A ball, a tire, a balloon. I guess a balloon isn't a very good example because the volume will change, so don't use a balloon. But maybe we use the bike pump example from our lab. Like I said, airing up a tire or a ball. Okay, but we see a different relationship here. Okay, again, we're going to show this: moles increase, pressure increases, and then this time the volume and temperature are going to be constant. So we're going to ignore those. Okay, same as before, we're going to sketch our graph. Okay, whoops, that's not very straight here. Okay, the amount of gas is our independent variable, pressure is our dependent. Okay, this time we've got a nice straight line. Okay, this is proportional. We're going to define this specifically as linear and proportional. Okay, so as the amount of gas increases, the pressure is going to increase at a consistent rate. Okay, particulate. We want to keep our volumes the same. I'm going to do my very best to draw similarly sized containers. If they are not exactly the same size, we're going to pretend that they are. Okay, this time the amount of gas changes. So again, I'm going to use a small number of gas particles. Let's go with like 4 to begin with, and then let's increase to, I don't know, 6. Okay, we don't need a ton of particles to show what we need to. Okay, some of you go a little crazy with the number of particles. Give me like 20 or more. We don't need that. Okay, temperature stays the same, so our number of whooshies are going to stay the same, but here it's going to be the pressure that changes. So let's go with 2 collisions in our first container to represent our lower pressure. Okay, put our movement lines to show that we're still moving. Okay, more particles are going to be closer together, which means they're going to collide with each other more, and they're going to collide with the container more. That's why we have an increase in pressure. So I need to show more than 2 collisions. So I'm going to start out with 2. Let's maybe go with, I don't know, 4. Okay, 3, 4. My other 2 particles that are kind of further away, those are just going to be moving. Okay, so let's keep track again here. Same volume and speed. Fewer particles and collisions versus more particles. Okay, well, fire alarm's going off, so we will stop there and I will be back in a moment.